right, everyone. Thanks for coming today. We have a special seminar from a special person here. I'm just going to shut this door. Michal Jakubczyk, at close enough. He's a friend and colleague of mine from Poland, the Warsaw School of Economics. He's currently on sabbatical right now. He's been at the Tippie School of Business in Iowa for about 6 months now. And now he's heading to Florida for some sunshine. He just wanted to get a full dose of cold weather to really make him look forward to Florida. So checking out some sites in Chicago. If you got some suggestions for Michael, he is up for deep dish pizza, blues bars, beef ribs. I mean, not just any slice of beef, but he wants beef ribs. So yeah, hang around after to give Michael all your recommendations. You've been based at the university in Warsaw for 8 years now, or how long?
Since 2007. So
2007, yeah. Right. So it was time to get out of Poland and come to the U.S. and see what goes on around the Midwest, I guess. Yeah. And like me, Michael said he just kind of closed his eyes and said, I want to go somewhere that begins with the letter I. And so it was somewhere in the Midwest, Iowa, right?
I just wanted to start loving corn.
That's right, yeah. So yeah, and I think that's how some of us found ourselves in the Midwest, and then it grows on you. But you said you're a European guy. It's like, that's right. So it's like you're definitely coming back for Disney World and other things. But I mean, it's the real outliers like me and Dan that end up staying. So what can you do? Anyway, I'm kind of excited about this talk, Michael, because it's quite a novel way to think about looking at cost effectiveness analysis. So please join me in welcoming Michael. Look forward to your talk.
Thank you. Looks like you said all the interesting things that I had to say. So thank you for that.
Not yet. He also has one brown eye and one blue eye. And they say that people with is that right? It's pretty rare. I don't know how
it's
rare
not that as rare as we thought.
Right.
Sad.
But people with two different eye colors have special powers, and by the end of the talk, I want you to figure out what it is.
Thank you. Thank you for having me here. Seeing Simon's always increases my quality of life. That's a good opportunity.
Funny, it diminishes everybody else's.
Yeah, I'm just seeing him for a short time. Really with him. Yeah, I'll just get started. So that's the last piece of work I have to get done before I'm heading for my holidays. It's sure that that's the last piece of work I'm having done in the States. So thank you for this nice opportunity. That's the topic, is using fuzziness to describe preferences towards willingness to pay, and then using cost effectiveness analysis. It's what I've been doing for a couple of months now. And well, we all know that we need to squeeze as much of an idea as we can in terms of computation. But I really do believe it's quite a natural approach when we're talking about preferences in healthcare. These are imprecise concepts, and it's difficult to really put a value on such things. So I do believe it's an idea that we should pursue and see how it can work. So in case I don't make much sense when I talk the rest of the slides, here's an overview of what I wanted to say to you guys today. So of course, I guess I don't know background individual, but I guess we're all aware that when we compare health technologies, we need to look at cost and effectiveness. And then we basically need to put, we need to do some coefficient trade. We need to put a price on an attack. Right? We need to have a monetary value of an attack, and it's difficult to do that. So we need this willingness to pay, and we also need the willingness to accept, but we don't really know what value to use. So it comes to me that it's natural to think about this as an imprecise concept. But if we are to support decision making, we also need to make this imprecise concept as formal as possible, because we need decisions to be transparent. So we need to somehow be precise about an imprecise concept, which is what I'm trying to show here. And when we build a framework, how to support decision making, and it took me some time to think about that. What I'm talking about now today is like the third paper in series. The previous work is quoted there. So we started with thinking about fuzzy preferences and only comparing two technologies. But then the choice is often made from more than two technologies. So we need a more powerful framework to do that. So when we build a framework, we need to actually estimate the fuzzy preferences. We need to know quantitatively what these preferences are. So then the statistical part comes in, how to estimate what our fuzzy willingness to pay is. And I'm also going to cover a bit some statistical methods I think might be useful here. And the last thing is that in the end, the decision is always crisp, non-fuzzy. You either finance a given technology or not. So the question is, do we gain anything by using all this fuzziness in the process? And I just hope to convince you that we gain some things. Okay, so let's by the way, of course, if you have any questions as I go, just go ahead. I guess that's the way we do it. Fine. Okay, perfectly fine with that. So the setting is as follows. We want to compare n decision alternatives, health technologies. I will either denote them with some subscript or with capital letters. And I assume they're all characterized by two parameters only, which is an expected cost and expected effect. So we just have two numbers behind describing each health technology. These cost and effect are usually that can be illustrated graphically in what's called the cost effectiveness plane, where we have the effect in the horizontal. I'll just use this so that it shows on both screens. So we have the effect measured on the horizontal axis and the cost measured on the vertical axis. And these cost and effect are measured relative to some status quo, which is the technology we would be using if we make no decision. It doesn't have to be like leaving patient to die. It can be some current standard. And for now on, for most of the slides, I will neglect uncertainty altogether. So I just assume there are two numbers describing each technology. So then the way the decision is made in cost effectiveness analysis is just you multiply the effect by willingness to pay to translate it into monetary terms. You subtract the cost and you get, voila, what's called the net benefit of using an alternative I. And of course, you want to select the alternative that maximizes this net benefit. In cost effectiveness plane, it can be nicely pictured graphically. Willingness to pay is simply depicted by a line whose slope measures the willingness to pay. So the steeper the line, the more I'm willing to pay for a unit of effect. And then maximizing the net benefit simply means selecting the technology which lies on the lowest line. The lower I can go, the more net benefit a given technology gives to me. So in this example, I should select technology B because it offers the greatest net benefit. It lies on the lowest of all parallel lines with the slope denoting my willingness to pay. Okay, does it make sense? So some problems would arise if I started to talk about technologies which are in the left part of cost effectiveness plane, in the third quadrant, when I'm losing some effectiveness but I'm saving some money. Then actually I have to ask myself how much I demand to accept the loss in effect. So then I'm talking about what's called the willingness to accept, not willingness to pay. And we don't have to agree it's the same value. Maybe when we are buying health, we are willing to pay a different price than what we demand when we are selling health. And there have been such claims in the literature, and there's been also some suggestions how to do it. I'll come back to that, whether we have this what's called the willingness to pay, willingness to accept disparity in the present context. So that's basically the starting point. It sounds so easy, except for one fact: how to decide about the willingness to pay that. What to put in the equation to calculate the net benefit. And there are many approaches we can use in the literature. Some of them use stated preference and just ask people how much would you be willing to pay for an extra device in your car to reduce the risk of you doing that in the next year by 0.01. Or some can be the revealed preference, like we can have a look at how much people are willing to buy for smoke detectors, or how much bigger wage they demand to be hired as miners in coal mines and things like that. In health technology assessment, what has been used is to look at some benchmark technologies like kidney dialysis and say, hey, we are willing to pay for that. That kind of tells us what value we are putting on life. In some countries, in Poland, where I'm from, there have been some arbitrary rules implemented by law, like in Poland. 4 years ago, they decided, okay, let's just take 3 times the annual gross domestic product per capita. Let's use this as a value of life. That's really, in a sense, cute, because I know the price of 1 year of life in full health in Poland is worth 125,955 zlotys. There's an exact number behind it in Poland. That's hilarious in a sense. On one hand, it's very useful. It's so transparent then. On the other, it's hilarious. We don't feel natural about health having an exact price. And this very motivates my research, that you cannot think about this as a precise, as a crisp concept. So in the literature, it turns out when you have a look at published studies that the standard deviations in brackets are of the order of magnitude of the mean values. So you can see how much variability there is in the value of statistical life. And let's just jump to reasons for that. So first of all, we have no market experience for buying health. At best, we are buying health services. We cannot say, oh, I just bought one quality adjusted life year a year ago. It wasn't as good as I expected. I must have overpaid for it. I don't want to pay that much anymore. There's no relevant market experience we can refer to learn our willingness to pay for that. Another thing is ethical consideration. So how would we feel as human beings if someone were refused treatment because the cost of one quality adjusted life, one quality, exceeded the threshold by $1? That's inhumane, right? That doesn't feel right. Putting a precise value on health just feels awkward in a sense. So like thinking about all that, I thought let's use fuzzy sets for a change and see where it leads us. So I'm sorry if you're all aware of what fuzzy sets are. I decided anyway to do a short introduction of what we saw just in case.
I don't think most people know what fuzzy sets are.
No? Okay, so it makes sense to go through that. So, like regular sets in mathematics are a collection of objects. Like we can have a collection of apples in this room. It's empty apparently. Collection of Coca-Cola cans. It's clear whether something belongs to a set or not. With fuzzy sets, which were discovered or invented 50 years ago by Lofty-Zadek, he said, okay, there are some things that just partly belong to a set. Like maybe let's directly refer to the example over here. Let's say we're talking about the temperature on a cold winter day. And I'm sorry, I put it in Celsius just to have my revenge on you Americans, because I really went through a hard time learning all the ounces and inches and miles and MPGs and stuff like that. So think in Celsius terms for a while, okay? 0 is freezing. It's so much easier, makes so much more sense in Celsius. So what's the cold winter day temperature? Is above freezing a cold winter day temperature? Not really. Is minus 20 Fahrenheit cold winter day temperature? Yes, for sure. But then if we start thinking, okay, is 25 Fahrenheit a cold winter day temperature? Kind of is, right? We start having values which only to some degree belong to the set. So when I talk about the set of temperatures that I would think temperatures of the cold winter day, I have some elements which clearly belong to a set. So these are the temperatures which clearly belong to this set, which is marked by the fact that they have what's called a membership function equal to 1. For sure, they do belong to the set. There are some temperatures above freezing which clearly do not belong to the set. This is not a cold winter day temperature. It's above freezing, right? And there are some temperatures which have some in-between value, of a membership function. So we can see, we can do the same thing for health. Does it make sense to pay $10 for a quality? Of course it does. As a society, I mean, right? Of course it does. Does it make sense to pay $100 for a quality? Of course it does. Does it make sense to pay $1 billion? Of course it doesn't. We cannot afford it as a society. Do we feel there will be borderline cases? I guess we do. Whenever we feel there will be borderline cases, it makes sense to think about fuzzy sets. And what's nice about it is that it comes with a whole package of mathematical operators you can use. You don't have to reinvent anything. For example, we can say that we can have a similar graph. What percentage of the sky would have to be covered in clouds so that we call a day cloudy? If it's 0%, of course it's not a cloudy day. If it's 100%, of course it is a cloudy day. If it's 50% of the sky covered, it's kind of a cloudy day, right? So then we can combine these two and we can ask, is it a cold and cloudy day? So we have to use the AND operator. And fuzzy logics gives us automatically tools how to work with fuzzy sets. We don't have to think about anything new. We just, when we accept to go fuzzy, it comes with a whole toolbox, and that's very convenient, right? So it's a mathematical formal way to talk about imprecise concepts. It comes with a well-established toolbox how to do things, how to use AND, OR, implies, not, all kind of things you may want to do with your data. Yeah.
So when we're thinking about fuzzy sets, just from a, well, when we're thinking about fuzzy sets, is it that different individuals view these as being different values, or is it an individual can view it depending on the
Yeah, thank you for this question. Yeah. So there are different interpretations of fuzzy sets. So this kind of ontology is being discussed. I'm thinking about it per individual. Like, do I like tomatoes? It's not like, do people like tomatoes? What fraction of people like tomatoes? It's, do I like tomatoes? I kind of like, well, I love tomatoes, but do I like pears? I kind of like pears. I don't really love them. I like, it's not a probabilistic assessment. Like the best, I mean, the example I love most to show it's not a probabilistic concept is when you take a bottle of water and you take some, mud from the street. You add some mud to the water, just a little bit. Is this water clean? Right? If you just add a little bit of it, you know how much was added. It's not probabilistic. We're not estimating the probability there was some mud added. It's simply, it's not entirely clean, but it's not entirely dirty anyway, right? So I'm talking about each individual. So then, of course, individuals can have different perception. We have to average this out, and this is what I'll also be talking about if I have time, because I always take too much time. So it's per individual, but then the averaging out also comes into picture. So it's obviously subjective, right, as written here, which is not a bad thing, because subjectivity is in cost effectiveness analysis anyway, like quality of life concept. It's very subjective, so it's already there. So what I'm thinking is, when we talk about this cost effectiveness plane, maybe we should really be thinking in fuzzy way. Let's have a look at this graph. So we have the effect and the cost. So now, when we think fuzzily, we say, okay, of course I like technologies which are here, because they give me more effect and they give me some savings. That's obvious, which tells me membership function 1, I like this technology. I mean, the answer to the question, should I be willing to accept this technology? Yes. That's for sure. Technologies which increase the cost and lower the effect, of course not. Now, technologies which force me to make some trade-offs between effect and cost. If I get lots of effect for just some small cost, I would be willing, for sure, I would say, yeah, I agree, it makes sense to use this technology. If I gain little effect and have to pay a lot of more cost, I would definitely disagree. But there is some gray area in this graph that I say, okay, I kind of see a point using this technology, but I also see some downsides to it. I'm not entirely sure. So that's like the ontology behind this concept, that we have this fuzzy representation of preferences in cost effectiveness plane, where there is some gray area in between. What I assume in the rest of the talk, it's a bit strong, but it's typically taken in cost effectiveness analysis is that my preferences are constant on all these rays stemming from the origin. So if I say that the trade-off 2 units of effect for 1 unit of cost is something I surely agree is acceptable, I will also agree the trade-off 4 to 2 and 6 to 3 and so on and so on. So these preferences is constant on rays stemming from the origin. If this preferences is constant along the rays, actually I only need to determine my preferences along this line, because then I will be able to project it radially on the whole first quadrant, and I need to learn my preferences on this line, and then I will be able to project it radially there. So what I need to do, I need to assess my willingness to pay, how much I'm willing to pay for 1 unit for 1 quadrant, and I want to do it fuzzily. So we came up with a survey a year and a half ago. We conducted it between 27 members of the Polish Pharmacoeconomic Society. I know that Poland is far away. It's not aware how things are going on there, but actually we are kind of advanced when it comes to health technology assessment. It's really been lots of that there's this public agency which is overlooking all the reports, and there's lots of awareness about this process. So we decided that these data are pretty good. So we asked these experts a couple of questions. So first 3 questions were just to see if they agree we need some willingness to pay threshold, and should it be publicly known. And generally they agreed strongly that, yeah, we need some threshold to make decisions. So they were aware it's needed. Then we asked, and these are 2 crucial questions, we asked 2 questions for some cost increment. For a 1 unit effect increment, you get 1 quality more, and then consider different cost increments. Do you think this technology should be used, should be accepted, should be publicly financed? And we used different levels of cost increments, and for each level of cost increment, the experts had 5-point Likert scale from totally disagree to totally agree, how much they feel that this trade-off is acceptable. Then same thing for willingness to accept. If you lose 1 unit of effect and then you make different levels of savings, how much do you agree it should be accepted? I will present the results in the next slides, but before, we asked 3 more questions. One was, okay, just think out what your willingness to pay is. Just write down a range of numbers. If you cannot decide about a single number, just give us a range of values. And on average, people gave us the range between 90,000 and 125,000 zlotys. 4 zlotys is $1 approximately. And then we asked, okay, if you provided a range, just give us a single number out of that range that you think is the most credible to you. And they gave us this value. It will be important in 2 slides what they gave us in that form. So we used 2 forms of elicitation. One was the Likert scale for various levels of cost increment. Another was a direct elicitation. We directly asked for willingness to pay. Now, it's a messy figure. I'll explain what. So on this axis, we have different cost increments in 100,000 zlotys. So for example, this value is 100,000 zlotys for 1 quality. Now along this axis, we have Likert scale from totally agree up there to totally disagree down here. And these circles represent the fraction of respondents. So we can see that the more we have to pay for 1 quality, the more people disagree it should be done, because it goes down, right? Simply. Now, what's important? These lines represent jumps. When someone jumped from totally agree to totally disagree. There was one person who was totally crisp, not fuzzy. Up to a certain value, this person said, I totally agree, we should pay this much for 1 quality, and then suddenly jumped and say, I totally disagree though, we should be paying this much. That's a totally crisp person, one of them in the whole data set. The rest of people went gradually from totally agree to totally disagree, sometimes making smaller jumps. Almost half of the people used the middle category of I don't know if I should be willing to accept that trade-off that you are presenting to me. And some of them, these horizontal bars present, these are per individual now, these horizontal bars present the ranges of values for which a given respondent say, I don't know. So some people said, I don't know for quite several values of delta C, right? They kept on not knowing if they are willing to accept this trade-off. So there's the story. So basically that made us believe that there is fuzziness in how people think about willingness to pay. Now here's another graph. I'm sorry that's quite interesting when talk about willingness to pay, willingness to accept disparity. So what we have here, again, on the horizontal axis, we have the cost increments we are asking people about. On the vertical axis now, I translated the Likert scale from 1 to 5 to 0 to 1, just to have it to interpret it as the membership function. Again, 1 means totally agree, 0 means totally disagree. And then I just averaged out the results for individual respondents. This line with black dots shows the willingness to pay. So the bigger cost we are considering, the less people agree we should be accepting this. The white line represents, the line with this white dots represents the willingness to accept. So the more savings we have, the more people agree we should be willing to accept that trade-off. What's important are these two vertical lines, dashed lines. So what they show is they show the results of this direct elicitation. Remember, I told you that we also ask people, what's your willingness to pay? Give us a range, direct. And that's the result of this question. So what is notable here is that when asked to freely report their values, people tend to report values towards which they are strongly convinced. So for example, this range ends about 125,000 zlotys. But when you consider the value 130,000 zlotys, the people on average still rather accept it as an accepted value to pay for one quality, even though it was beyond their range. So when asked directly, people try to play it very safe and report values towards which they are really confident. So coming back to this cold winter day temperature, if I asked you what's a cold winter day temperature, you'd probably give me a very low temperature just in case. You want to report something you truly believe it's a very representative example of a cold winter day temperature. This means that the elicitation method matters. How you want to elicit the preferences is going to impact your results. And the Likert scale and the direct elicitation will give you different results. These are the results, by the way, that I have with my co-author of the previous paper. And that's why I keep on saying we. So unfortunately, we did not ask the same question for willingness to accept. But if the same phenomena occurs, then we would expect people to report freely their willingness to accept the values which are much higher. Again, which are associated with great confidence, so they will be around here. And that can explain, in a sense, the willingness to pay, willingness to accept disparity, even though these two lines look kind of as mirror images of each other, in a sense. Because people, when freely thinking, when freely reporting their values, tend to hit the values towards which they are very confident, this disparity may show up because of the way of elicitation rather than true difference in preferences. So these are some additional findings. Okay, so let's go back to cost effectiveness analysis now. If we accept the fact that willingness to pay is a fuzzy concept, the bigger the value, the smaller my conviction. It's a good deal. And how to do it? How to make decisions based out of it? So just to as a reminder, when we had crisp willingness to pay, what we did is we simply translated the effect and the cost into crisp net benefit, a number. Now that we have fuzzy willingness to pay, we end up with a fuzzy net benefit. So now how much I gain by using a given technology is not anymore a single number. It's rather a fuzzy concept. And in this graph, I have a couple of health technologies. And this is what the fuzzy net benefit would look like for these technologies. The horizontal axis measures the net benefit, the value. The vertical axis measures the confidence I have that using a given technology gives me this net benefit, or is as good in monetary terms. So for example, if I look at technology D, which is represented by a black line, it's this line, I don't anymore know it gives me a net benefit of 2 monetary units. Now I say, okay, for sure I gain at least 0.5 because my membership function is 1 for 0.5. And for sure this technology doesn't give me more than 4.5 because my membership function then is 0. It decreases to 0. But in between, I'm very convinced it gives me at least 1. I'm quite convinced it gives me 2. And I'm only a little bit convinced it gives me 4. Okay, now I have a fuzzy measure how good a given technology is. But how to pick the best one then in this graph? When I was comparing numbers, it's easy to select the biggest number. How to select the best fuzzy number? We have to, in a sense, try to select technology which is the most to the right, because it is associated with the biggest net benefits, but there's no single line which is anonymously the rightmost one. So what I suggest, and now because my time is going faster than I thought, what I suggest, and this is the good thing about fuzzy sets I was talking about, it comes with the whole toolbox, how to do some mathematical operations. So there was a discussion in fuzzy sets, how to select the biggest set, how to do all the mathematical operations there. So when you use some standard ideas in this literature, like weak inclusion or Orlovsky score, I'm going to skip the details. I find out that the method you can use is simply look at the 0.5 line. Kind of go for a compromise. Because if a technology is best when it comes to this, in a sense, median point, it means you neither want to, just like, in a sense, it's similar to median voter theorem. Like you need to convince a median voter because you won't be overruled up or down. If you select a technology which is best when it comes to the horizontal 0.5 line, it means you will not then want to go to a technology more costly and more effective, but you will also not want to downgrade to a technology less costly and less effective. So there are some mathematical reasons which would require some technical discussion to select a technology based on this. So in this case, we would select technology C, and to apply this method, it actually suffices to calculate the willingness to pay, the value of willingness to pay, with which the respondents equally agree and disagree that they would accept this trade. So we need to find a number with which people find as many reasons to say yes and as many reasons to say no, that this is a good price for health. Looking at it graphically, we need to find a value. We need to find a value for which people are halfway through. Okay, this discussion brings us here. We need to find one number for which people somehow went from totally agree to totally disagree. But how to? So this is where this part between objects, between individuals. This is this part when the discussion about between individuals differences comes into play. How to determine a single number? Where is it that the population on average as a whole change their mind from totally agree to totally disagree? How to estimate that? And so this is what was largely the contribution in the last paper. I proposed 3 methods how we can think about estimating this median willingness to pay based on Likert-based estimation like that, I guess I'll just present one method that could be used. The other two are in the paper in case you want to have a look. So the idea is the following. Let's imagine there is, when we think about the population, let's imagine that for each cost increment, there is some average conviction in the population. There is some average conviction level in the population. We should accept this cost increment. We are looking for such a cost increment for which our population level average conviction is 0.5. Okay. Now, if we know this, for a second, let's assume we know this median willingness to pay, for which our average population level conviction is 0.5. But we differ as individuals. Some of us may say this is definitely acceptable. Some of us may say this is definitely unacceptable. It's too much to pay for health. But if on average we are halfway through, then on individual levels, half of us should be above, half of us should agree, and half of us should disagree. So we are looking for a point on this axis for which the distribution in vertical axis is symmetrical along this median answer. Okay, so for example, is 50,000 zlotys this point? No, because all the answers are in the upper part. Is 500,000 zlotys the answer? No. Most of the answers are down here. Where is such a value that we are almost equally distributed up and down of this graph? So we need to test statistically for the symmetry of the distribution in the vertical axis and see for which cost increments we would say the distribution is symmetrical. And there are two tests we can use. I use the Dijkstra test that was invented and published in 1995. The funny thing is, it was published by a guy from Iowa, University of Iowa. I didn't know that. When I was looking for a proper test to use on my data, I found the paper and I read the affiliation and wow. Unfortunately, his guy is dead, so I couldn't talk to him, but that was a nice thing to discover about Iowa. So we can use the Dijkstra test. We could also apply the Mann-Whitney test, but applying it to these results, to my data, gives the following results. For willingness to pay, I couldn't reject the hypothesis, the null hypothesis that the distribution is symmetrical for these two levels. This is in thousand zlotys per quality. So I'll just go back for a second. So for 125 and 150, this distribution of points is so symmetrical that a formal test does not reject the symmetry. I have no reason to disbelieve that this is the median willingness to pay in the population I was testing. For willingness to accept, I don't have a graph here, it's somewhere further on. I couldn't reject a null for a wider range of values. There's much more statistical noise. I can just skip ahead. Yeah, this is the willingness to accept data. Now it's increasing, of course. The more saving I offer, the more people agree it's acceptable. So there's more statistical noise here, and I couldn't reject a null for more values than with willingness to pay. One value coincides in both sets, so we cannot clearly say there's any willingness to pay, willingness to accept disparity when thinking about this as median willingness to pay and median willingness to accept. So the other methods which I used, I won't go into them. I'll just show you the results. I decided to use three different methods. One of them was hypothesis testing, which just presented. Another was Bayesian modeling. Another was frequentist approach. The other two are nice because we end up with a point estimate with an actual value. Here I just have a set of numbers I did not reject a null for. In the other methods, I get the final estimate, a number, and a confidence interval or a credible interval. So it's maybe some of us will like it. So I'll just present the results. So when you employ the other methods that we wrote on the table, willingness to pay or willingness to accept, you see that the results for willingness to pay and to accept are very similar. right? There's no reason to think there is some systematic tendency to have a greater median willingness to pay than willingness to accept, at least in the data I had. So when you think about this as fuzzy notions, somehow the disparity seems to disappear. I'll just maybe skip that because I understand we're aiming for 10 past, right? To end.
20 past.
To-
Yeah,
to-
we just wanted a few minutes of questions, so you have to dismiss it 20 after.
Okay, so let me just present 2 slides then. Okay, so in a sense, we started with fuzziness, fuzzy willingness to pay. Then I said we need to make a decision, and the best way is to just look at the line at 0.5 level, like median thinking. We had to estimate median willingness to pay and median willingness to accept, which led to some statistical methods, and we get our estimates, but they are with some confidence intervals, so they are given with some uncertainty. Right? So we started with fuzziness, we ended up with uncertainty. This uncertainty is of stochastic nature, just like every estimate. Some normal distribution behind or log normal, right? So we traded off the fuzziness for stochastic uncertainty now. And I would say it gives a quite nice and intuitive new insight in sensitivity analysis, in cost effectiveness analysis. So because if you've done the cost effectiveness analysis, the sensitivity analysis there, then you are used to these scatter plots, right, where you show, okay, I don't really know what is the effectiveness of new technology, what is the cost of new technology. I just have some cloud of points here, and I don't really know which one it is. So with CRISP, given as number, willingness to pay, you just project these points onto this axis to calculate the net benefit. And if you move this cloud of points farther away from the origin, nothing changes, which is somewhat surprising maybe. If you say, okay, it's not now in this graph, I trade off on average 2 effect units for 2 units of cost, but if I just moved it somewhere here and I would be trading off like 20 units of health for 20 units of money, still, if I know the willingness to pay, I just project it along parallel lines, this outward shift doesn't make any impact. Now, if I say, I estimated the median willingness to pay, but I don't know exactly what's the value because I only estimated it with some Bayesian methods. So now I don't project the point along parallel lines. I kind of have a fan here because I don't know what my willingness to pay is. I kind of have uncertainty what is the slope of lines I should be using. And it gives me what I find quite intuitive, that the more I move technology outwards from the origin, the more uncertainty I have in the problem. And I find it very intuitive because if I think about technology where I get 2 effects for 2 costs, okay, I'm trading off at small numbers. And then if I have technology where I trade off 100 units for 100 units, wow, I really get a bit afraid I'm making a bad decision there because it means big numbers behind. So I like the idea that when we have uncertainty in willingness to pay, it makes us vulnerable when we have to make big decisions involving big numbers behind, which is something that was not really present in this literature. So to sum up, and this is like my credo maybe, but what I really believe, that willingness to pay and willingness to accept are fuzzy concepts. That's simply how we think about measuring such an difficult thing to measure as health. So it's kind of, I would rather expect rationale not to use fuzzy logics and fuzzy things behind than the rationale to use, because it's simply a very natural, for me, starting point. It's this I would say that modeling in this way gives you more face validity because you're using building blocks which are more ontologically motivated in my view. Using this, I'm going through this story in a very quick pace here, apparently, too many slides. But it gives us some formal rationale, for example, to use this median willingness to pay. So it gives us some rationale. What, even if we need to end up with a crisp decision, it gives us some story what exactly this crisp value should be and how to estimate it based on data as we collect it. There is some formal thinking behind. It also provides this new effect and sensitivity analysis that we don't like the fact that we have to trade off big values against big values. And it also, in a sense, explains the willingness to pay, willingness to accept disparity, showing it's more an artifact of the elicitation method than a true difference between how these two membership functions are located. So what I'm planning to do and what I'm currently working on is we are trying to collect more data. We are starting a project in UK to collect data among experts there, how they perceive, because I'm kind of playing with the same data set of 27 people, so squeezing as much as I can from it. On the other hand, it looks like a good testing field, like test your ideas there, test your statistical methods there, and when they are refined, you can go and collect more data, like knowing. This also teaches me a lot how to design these questionnaires to collect data that then I can apply the statistical methods to. So we are now starting the project to collect data in the UK. I would say that this framework, this fuzzy net benefit and how to maximize it and what health technologies to select, it actually opens the door to let other types of fuzziness do. For example, utilities apply. When people are deciding whether they are on level 4 or level 3 in Europol, in EU5L questionnaire, it is fuzzy, right? I don't know if I'm level 3 or level 4, right? It's not clear cut. So it might be very natural to also measure the effectiveness in fuzzy terms. And then when you have the framework, the mathematical framework, then the standard fuzzy literature gives you immediately the way how to multiply fuzzy numbers, how to add fuzzy numbers. So it's not a problem formally to take the fuzzy willingness to pay and multiply it by fuzzy increment in effectiveness to get a fuzzy net benefit. So once you have a framework, you can start making all the things funny. So that fuzzy. So that's kind of a thing to think about in the future. And I'm also currently working on different methods of estimation, because here I only just showed how to estimate this median level, but you also sometimes may wish to estimate the whole shape of the membership function, not only one slice of it, but how it looks in general. So that's currently what I've been doing in the past couple of days, actually, how to estimate the actual shape of a complete membership function. So trying to win with the fuzzy concept.